Hello, so in this module, we are going to have a look at the AC response of the amplifier that is shown. So in our previous model, we talked about the CC common collector mode of the transistor, and we stated that it is also called as emitter follower. And we also call it as a voltage buffer. So basically, buffer is a circuit that helps us to transform the impedances at the input and output side. And this is a voltage buffer or in a common collector mode where we apply input to the base and take the output from the emitter. This is an emitter, this is a base, and this is a collector. And now we are going to simulate for the Bode plot, and we know that the V output is V in minus VBE. So if your V in increases or decreases, the output also increases or decreases, and it is always one drop less than the input voltage. So this VBE is always constant, except there is a change in temperature or what. So with the values chosen of the components and the transistor I have chosen is about 2 and 2222, with a beta factor from his SPICE model is about 200. So what I have done here, I have actually kept the same voltage source that I used to perform DC analysis in our previous module, and refer to that if you want to understand the operating principle of this circuit. So you see the DC value has been set here to 3.2 volts so that I have biased my transistor in an active region. And here AC amplitude for the AC analysis, I'm using the small signal AC analysis. The AC amplitude, I'm setting it to be 1. And with the DC biasing, base at 3.2 volt, collector at 5 volt. You see, this is the 5 volt that is coming here, and then emitter is 3.2 minus 0.65 or 0.7. That is about 2.5. That is my DC. So this diode is forward bias, this diode is reverse bias, and transistor is set to be operated in an active mode of operation. So I am going to now put the AC analysis. So I'm using the SPICE syntax like this, dot AC, decades, just right click, I show you this. Type of sweep is decade, number of points are thousands, start frequency 1, end frequency, let's say 100 mega. I click OK, and I click go here to simulate. I have this graph right here. And before that, let me clear all the drawings. And now I am going to plot this output right here. So as expected, I see a gain of, it's minus 93.6 millidecibel. So it's not just approximately 0 decibel, because I said the voltage gain of this circuit is approximately 1. Here we have seen that, right? So we've said that small signal voltage gain is which is the ratio of V output divided by V in, is approximately 1. And R in for this circuit was beta times RE, and R out of this circuit was RS in parallel with RE divided by beta. So it can be approximately equal to RS over beta, where RS is the source impedance, which is very less than RE, right? So RE is, let's say, 1 kilo ohm, and source impedance is about 1 to 10 ohm. So that's how you can approximate to this expression. So right now you see we are simulating this voltage gain, and it is close to unity. So I right click here I will right click here and I will choose representation to linear, and I will see I have like 989 millivolts, so approximately 1000 millivolts, so 1 volt. And it is all the way constant till the minus 3 dB point, which is right here. Let me draw it. So here it is about minus 3 dB point is not seen here. In fact, we have to go longer in the frequency range, right? So, but it's okay. We just see that the gain is constant up to 10 megahertz. But I am not going to use it as a voltage amplifier. This common collector stage is not used as a voltage amplifier. Rather, it is used as a voltage buffer. So here is your voltage buffer, common collector, where R out is low, very low, given by this expression, and R in is very high, given by this expression. Beta is 200, RE is 1K. So you can see that it's about 2000 kilo, so 2 mega ohm right here. So this voltage buffer is placed between the two circuits where impedance matching is required. So if you have a circuit here, let's say circuit number 1, which has a very high impedance, so you can place the voltage buffer to match to its impedance R high. And then if you want to drive a load which requires a very large current, so R out being very low for the CC, can be able to drive supply heavy currents to the load RL. And that's how you do the use of this one. How about we try to simulate the current gain of this circuit? So let's say I don't want this, or maybe I would add the plot pane right here. And let me, before that, clear the drawing. And now here I will just say add trace, and I will take the ratio of the output current. So output current is my IE divided by input current. I of V1. So let's see how much is that 1. So it's about 1, or in the decimal, I have about 0 dB. Yeah, so why is it giving me just a gain of 1? So maybe let me just do here. For example, I delete this and add trace, and then the output current is here divided by, if we simulate the base current, maybe. Yeah, so is basically your the current gain of this transistor would be like this or not. Let me cross check that. That's correct. Correct. In fact, I should simulate it to be output current is IE and input current is IB. Actually, theoretical current gain of this transistor is written as beta. This is the current gain, which is beta. And beta is very greater than 1. So for this transistor, beta is 200. So the current gain that we see here, we can plot. Output current is your I out, which is your IE, and input current is your base current actually, right? And that is IB. So that's why we take a ratio of it, right? Neglecting the base current is in fact beta is IC over IB, right? And we can say that IC approximately equal to I right here. So we have a gain of about 40 dB, which is constant up to the frequency about 200 kilohertz, and that's our the first pole. That is first pole frequency. Thereafter, the gain drops at minus 20 dB per decade. So that's quite useful analysis that we have done. Okay, and hope you like this video. Click on the comment section. Tell me what you think about it. Till then, wish you happy learning. And we can also try to simulate the transient response of this amplifier. Try to see how your current amplification or voltage amplification is done. So refer to our previous videos. Till then, wish you happy learning.